Hello everyone, welcome to my lecture. And myself Viswa Ganesan from Department of Chemistry, Tirthangal Nadar College. So in this lecture, we are going to discuss about solution. This is the topic which is from physical chemistry. So what is meant by solution? So in our day-to-day life, we may come across many different kinds of solutions. Say for example, the paste which we are using, or even a soap, or the soft drink which we are drinking, or any kind of alloy like a gold or steel. All these components are called solutions. Then what is mean by solution? What is exactly the solution is? Look at this definition. It says that a homogeneous mixture of two or more substances. So this is a clear definition for a solution. Homogeneous mixture of two or more substances. What is this homogeneous? Nothing. So the mixture is uniformly mixed with each other. The substances are uniformly mixed with each other. So that kind of mixing is known as homogeneous. So whenever you have a homogeneous mixture, that can be denoted as a solution, right? Then in solution, uh, since it is a mixture, we may have two or more substances, right? So two substances means one would be smaller quantity, which we say as a solute. Another would be large quantity, that is a major quantity, that is known as solvent, right? So in the mixture, the substance which is present large quantity is known as a solvent, and the substance which is present smaller quantity, that is known as solute, right? Suppose if you have more than one solute, in that case one must be a solvent and the rest all are should be a solute. All are should be solute, right? If you have only one solvent and one solute, that kind of solution is known as binary solution. That kind of solution is known as binary solution. And mostly in this particular lecture, we would discuss about only binary solutions. Only binary solutions, right? And during our discussion, we use the number 1 for representing solvent and the number 2 for representing solute, or we may use a letter uppercase A for mentioning solvent and uppercase B for mentioning solute, right? So slowly let's move to classification of solution. How can we do classification? So solution can be classified into 9 different types based on the physical state. So this is the classification only for a binary solution. Let's see, in a binary solution we may have a solvent, we may have a solvent, we may have a solvent and a solute, and a solute. Okay, the solvent can be in 3 different forms. Solvent can be in 3 different forms. It can be in solid form, it can be in a liquid form, or it can be in the gaseous state. It can be in the gaseous state. Similarly, solute also can exist in solid form or liquid form or in the gaseous state, right? So if you mix a solid solvent with a solid solute, you will get one solution. If you mix solid solvent with a liquid solute, you will get another type, second type of solution. If you mix solid solvent with a gaseous solute, you will get third type of solution. Same way you can, but in all these three categories, your solution, the physical state of solution would be a solid. Then that is known as solid solution. Same way you can mix a liquid solvent with solid solute, liquid solute and gaseous solute. Again you will get three different forms of solutions. They are known as liquid solutions. So that was clearly said here, right? Solid in liquid, or solid solute in liquid solvent, or liquid solute in liquid solvent, or gaseous solute in liquid solvent. Like that we can have three different solutions under the category of liquid solution. Then what about gaseous solution? Here the solvent is a gas which is going to be mixed with a solid solute or a liquid solute or a gaseous solute. So once again we can have three different solutions which are in the gaseous state. So in solid solution we can have three different types. In liquid solution we can have three different types. In gaseous solution also we can have three different types of solutions. So totally we can have 9 different. So the combination will give 9 different types of solutions. The best example for gaseous solution, the air which is a mixture of nitrogen, oxygen and carbon dioxide. In this, nitrogen will act as a solvent and the rest will act as solutes, right? And for liquids, so even the fog, smog, that the fog can be used as an example for gaseous solution. The foam which we are using, that also can be example for a type of solution. So let's move to the next topic, the concentration terms. What is this concentration term? Suppose if a person is has provided a salt, some amount of salt, and the question is, what is the quantity of salt? What is the quantity of salt? So the question is, what is the quantity of salt given? So since it is in pure form, one can easily use the balance and we can weigh the quantity of salt which was given, right? If the same salt dissolved in water, now after dissolving the salt in water, again the question is same, what is the quantity of salt? Now it is a little bit difficult to answer the quantity of salt, right? So in a mixture, if the quantity of one substance is asked, it is quite difficult to answer. So we need to perform some experiment. So since it is a difficult process, we can't use this kind of amount calculations for solutions. So that's why we are using different concentration units for mentioning the solutions, or for telling about the capacity of the solution, right? So the very first concentration unit is molarity. The very first concentration unit is molarity, which is indicated by a letter M. So molarity is nothing but N by V. What is this N? N represents number of moles. Number of moles. So what is this number of moles? Or how can we calculate number of moles? Here, if you know if you have the knowledge of calculation, that is sufficient to handle this particular concentration unit. Then how can we calculate number of moles? N. So N is nothing but N is equal to, here N is equal to weight by molar weight or molar mass. Weight by molecular weight or molar mass. So this ratio will give you number of moles of solute which is present in the particular solution, and V is volume of the total volume of the solution which is in liter, So number of moles, the ratio of number of moles of solute and total volume of the solvent. This simply says that molarity is nothing but number of moles of solute present in unit volume, or let's say in 1 liter. Number of moles of solute present in 1 liter, that is known as molarity. The next second concentration term, this also we frequently use in chemistry, chemistry laboratory, molarity, which is indicated by a letter small m. So molarity is equal to number of moles of solute divided by mass of solvent. Then again you know how to calculate number of moles. This mass of solvent should be substituted in terms of kilogram. Then we can say that molality is nothing but number of moles of solute present in 1 kg of solvent. So these two terms we have to carefully handle, because they have very minute difference. In the molarity, we have volume as the denominator, whereas in the case of molality, we are having mass in the denominator. So the volume which depends on the temperature. When you change temperature, volume would be affected. Volume may increase or decrease. But whereas the mass which is independent. So here number of moles as well as mass both are independent of temperature. That means molality is independent of temperature, whereas molarity is dependent on the temperature. Molarity would vary when you change the temperature, right? So this is the main difference between molarity and molality. One more thing, in the molality calculation we are using only solvent, whereas in the case of molarity we are using solvent as well as solute. Then the molality, the denominator of molality may be smaller than the denominator which we are using in the molarity. So molarity always smaller than molality. Now let's move to the third concentration term, mole fraction. Mole fraction, which is indicated by a letter small case x. So this mole fraction can be calculated for both solute as well as solvent. Already I said solute means we use the number 2, so we can use x2 as the mole fraction of solute. So x2 is equal to it is the term itself saying mole fraction. It is a fraction and its range is 0 to 1, always less than 1 and greater than 0, always less than 1 and greater than 0, right? Okay, so x2 can be calculated by using the ratio of, say for example, mole fraction of solute, which is nothing but n2 divided by n1 plus n2, that is number of moles of solute divided by total number of moles present in the solution. So this ratio, since the denominator is n1 plus n2, always greater than the numerator n2, so you will get this value always less than 1, right? So same way you can calculate mole fraction for x1 also. x1 is equal to n1 divided by number of moles of solvent divided by total number of moles of solution, that is n1 plus n2. This also less than 1. And in a binary solution, binary means we'll have one solvent, one solution, one solute. For a binary solution, the sum of x1, the mole fraction of the solute and the solvent, which is equal to 1. This relation is very famous. So for a binary solution, if you know mole fraction of solute, you can easily get the mole fraction of solvent by subtracting from 1, right? Okay, so if you know the mole fraction of solute, you can calculate mole fraction of solvent. So let's move to the fourth concentration term, which is mass percent. Mostly this kind of concentration term would be used in the medical field. This is denoted by the percentage symbol. So mass percent is nothing but it is the ratio of mass of solute divided by total mass of the solution. Mass of solute divided by total mass of the solution. This ratio will give you fraction of solute present in the solution. If you multiply by 100, you will get the value in terms of percent. And actually we say, since we are using mass here, this would be said by mass by mass percent, m by m, or we can use w by w percent, weight by weight percent. We can also use mole percent. Similarly, we can use volume percent. In terms of volume also, you can take this calculation. In terms of moles also, you can do this calculation. That will give you mole percent. If you use volume, you will get volume percent. If you use mass and volume, that we call it as W by V percent. W by, so how we are saying W by W percent, weight by weight percent, same way we can tell W by V percent, that is weight by volume percent. So then let's move to the sixth concentration term, parts per million. So the previous term which is said parts per cent, cent means out of 100. Okay, percent means out of 100. Here parts per million. Then the only difference between the mass percent and the parts per million is this term. In mass percent we use 100. In parts per million, I think million is nothing but 10 to the power 6, 10 lakhs. So parts per million is nothing but the ratio of mass of solute and total mass followed by 10 to the power 6. That will give you parts per million. Here not only mass, even you can use numbers, you can use volume of A divided by total volume, or number of molecules of A divided by total number of molecules. You can use any parameter to calculate this parts per million. But this particular unit we use when you have very small quantity of solute, particularly for reporting pollution, or for reporting impurities, or for studying impurities. We use this parts per million scale. Right? For either for measuring pollution means the amount of pollutant present in the air, amount of pollutant present in the water or present in the soil, which are very small quantity, will be reported in terms of parts per million. In short, this is written as ppm. This is written as ppm. So that's all about concentration terms. Let's move to the next topic. So we have 6 different concentration terms in chemistry. Particularly in solution, we handle all these terms. Then if you calculate this concentration term, that is known as actual concentration. So by using the given mass of solute and the given mass of solvent, one can easily calculate the concentration of any particular solution. So by using any of that concentration scale like molarity, mole fraction, mass percent, volume percent, or ppm, and that concentration is known as actual concentration. But the same concentration can also be measured by doing experiment. That is known as experimentally determined concentration, which we call it as effective concentration. The actual concentration is the calculated one. Effective concentration is experimentally observed one. The effective concentration, which is known as activity of the solution. The effective concentration is known as activity of the solution. The ratio of actual concentration and effective concentration. Effective concentration and actual concentration. That will give you a coefficient which is known as activity coefficient. So the activity and activity coefficient, these two are very important terms, and frequently we'll handle them while using the solutions. So that's all about introduction about on solutions. So let's move to the very first topic from the solution. The first topic is Henry's law. What is this Henry's law? This particular law deals a solution of gas in liquid. Gas in liquid. What is this gas in liquid? A gaseous solute dissolved. A gaseous solute is dissolved in a liquid solvent. Immediately the people will think that, is this possible to dissolve a gas into a liquid? Yes, this is quite possible. That's why all aquatic lives are possible. The fishes and other aquatic systems, since the oxygen is available, the molecular oxygen is available in water, the living system is existing in the water bodies, right? So even you can take an example of Coke. Whenever you open a Coke bottle, by the time you can observe the fishy sound coming out of the Coke bottle. That fishy sound says that the liberation of carbon dioxide. So enormous amount of carbon dioxide dissolved. Large amount of carbon dioxide dissolved in the soft drinks, and when you open the bottle, it will come out with the sound and bubbles, right? So gases are normally soluble in liquid, but the proportion may be smaller when we compare with the solid solute. Okay, so this particular the law which deals the amount of gas dissolved in a particular solution or in a particular solvent. So this gives you a clear relation between amount of gas dissolved and pressure which we are maintaining above the liquid, the pressure of the gas which we are maintaining. So pressure of gas is nothing but P2. Amount of gas dissolved. So already I said amount means we won't use in solution, we won't use the amount in terms of gram. Instead we use any one of the concentration terms, and here let's use mole fraction. So the pressure of solute, which is directly proportional to the mole fraction of solute present in the solution, which we can say that solubility. And you can frame now the simple equation P2 is equal to K into X2, where here K is Henry's constant. And by using this relation, one can easily fix the amount of gas to be dissolved in a particular solution. That can be decided by using the pressure. So by knowing this relation, one can easily fix the pressure to dissolve the quantity of the gas, right? So let's move to the next topic, Raoult's law. The next topic, Raoult's law. So this law deals a liquid solute dissolved in a liquid solvent. We can say that liquid in liquid solution. Liquid in liquid solution. So solute is liquid, solvent also a liquid. If the solvent or if both are volatile, then this we can make a relation between amount of pressure present above the liquid, which is created by the vapors of the liquid, amount of pressure versus mole fraction, as we did in the Henry's law. And this kind of relation we can make for both solute as well as solvent, since both are volatile. Here both may be volatile, solute as well as solvent, so both can may form vapors and will create pressure. So exactly you can make this kind of mathematical equation. So P is equal to x, this is nothing but x into P naught. Here P is nothing but the amount of pressure which is maintained above the liquid, that is equal to mole fraction and P naught. P naught is nothing but if you take a pure liquid, pure solute or solvent, and its pressure, its vapor pressure, that is known as P naught. The pressure created here by only A, that is known as P naught, or we can say here it's P naught A. It's P naught A, right? P naught is nothing but when solute or solvent which is in the pure form. Under that condition, the pressure which is created by the vapors of that particular liquid, right? Vapor pressure created by the particular vapor in its pure form, that is known as P naught. So this equation gives you a clear relation between vapor pressure and X solubility. So based on the solubility, one can easily find out vapor pressure, or based on the vapor pressure, we can get the solubility, right? Okay. So based on this particular Raoult's law, we can classify the solution into two different types, ideal and non-ideal. If a solution obeys Raoult's law exactly at all concentration, at all temperature, that is known as ideal solution. If the solution does not obey, then it's non-ideal solution. And here we have a list of solutions which are obeying Raoult's law. A combination of ethylene bromide and ethylene chloride is an example for ideal solution. N-hexane, N-heptane is also an example for an ideal solution. N-butyl chloride, N-butyl bromide, benzene and toluene, or combination of carbon tetrachloride and silicon tetrachloride, all are example for ideal solutions. If it does not obey, then it's known as non-ideal, or we can say that that is a real solution. And most of the real solution will not obey Raoult's law. Will not obey means will not give the proper mathematical relation P is equal to X into P naught. So this relation will not be obeyed by the real solutions, right? Then if it is not obeyed, then the solution will deviate from ideal solution or deviates from Raoult's law. That kind of deviation can be observed by making a plot. So look at this graph here. X-axis is mole fraction X, and y-axis is nothing but vapor pressure of solute or solvent. If you draw a plot between mole fraction versus vapor pressure, say for example vapor pressure of solvent, which is A, you will get a straight line like this. According to Raoult's law, you will get, so the vapor pressure of A proportionally decreases with its mole fraction. So when mole fraction decreases, the vapor pressure also keep on linearly decreases. That's why we are getting a straight line. Same way, if you do the plot for vapor pressure of solute versus its mole fraction, again you will get a straight line like this. Or even if you plot a graph between mole fraction of either solute or solvent versus total pressure, by the time also you will get a straight line. So whenever you get a straight line for the plot between mole fraction and vapor pressure, then you can say that the solution which obeys Raoult's law and can be an ideal solution. So this graph is only for ideal solution. This graph is only for ideal solution. Also we can identify the ideal solution by measuring delta V mix. Delta V mix, that is volume change during mixing. If this volume change would be equal to 0, then solution would be an ideal solution. Or we have one more parameter, which is enthalpy change during the mixing. If enthalpy change during mixing, if it is equal to 0, then also we can say that the solution is ideal solution. So for finding ideal solution, we have three different parameters. Either you can check Raoult's law by using this graph, or you can check it out delta V mix, or you can check it out delta H mix, right? So non-ideal solution, then the delta V mix not equal to 0, delta H mix will not be equal to 0 for non-ideal solution. Then they show deviation. The non-ideal solution will show deviation. Deviation means what kind of deviation? Look at this graph. The dotted lines are representing ideal solution graph, but for real solution you will get this solid line. So the dotted line indicates which is for ideal solution, but for real solution you may get a curve which lies above the dotted line. Curve lies, this is known as positive deviation. That means the vapor pressure will be higher than the expectation. So you will get the curves which are above the expected straight line. That is known as positive deviation. Since the deviation is very small, this is known as small positive deviation, or we say that type 1 solution. We say that this is a type 1 solution. If the deviation is large enough, if the deviation is large enough, that means the pressure which is higher than the P naught and P naught A and P naught B, by the time we call it as large positive deviation. This is also a positive deviation, but the deviation is quite large. The deviation is quite larger than the maximum pressure. Then that is known as large positive deviation. We can also, so this large positive deviation is known as type 2 solution, which is known as type 2 solution. We can also have type 3 solution, which is nothing but negative deviation, Look at this graph. You can see the solid line which lies below the straight line, which lies below the expected straight line, right? So then this is known as negative deviation. The expected, the actual pressure would be smaller than that of expected pressure, right? So this is type 3 solution. So based on the Henry's law and as well as Raoult's law, we can classify solution as type 1, type 2, type 3. that is small positive deviation, large positive deviation, large negative deviation. So the some basic things we have covered in this lecture. In the next lecture, we'll extend our discussion to some of the examples for type 1, type 2 and type 3 solutions. So thank you viewers for watching this video.